Have you ever paused to truly consider the invisible ballet that unfolds every time your computer saves a document, loads a game, or even just accesses a simple configuration file?
It happens so fast, right?
Exactly. It's not just instantaneous magic, not just a flicker of light on a screen. Beneath that smooth surface lies a meticulously engineered system, working in ways that are, well, far more sophisticated and often surprising than you might imagine.
hmm There's a lot going on under the hood.
Okay, let's pull back the curtain on that invisible ballet then. Today, we're taking a deep dive into the fundamental world of basic concepts of file I/O within the Linux operating system.
A really core topic.
Totally. Our guide for this exploration is Stuart N. Weiss's System Programming in Linux, a hands-on introduction, a phenomenal resource, really. It's designed to give you the foundational tools and critical insight to understand what's really happening when your software interacts with the hardware.
It really is a great book for that.
It's truly a gem for anyone wanting to move beyond just a superficial understanding and get closer to the metal.
And what's truly fascinating here is that you don't need to be an aspiring system programmer to find immense value in this deep dive. Not at all.
Right.
Understanding these basic interactions between your software and the operating system is utterly essential for, well, pretty much anyone who uses a computer or who hopes to build anything with one.
Yeah, it's foundational.
It's about gaining a deeper appreciation for the bedrock of almost everything you do on a computer. From the simplest text editor saving your notes to complex server applications managing vast databases or even the operating system itself booting up. File I/O is the unsung hero,
Always working behind the scenes.
and Linux handles it with remarkable elegance, power, and surprising efficiency.
Our mission today is to thoroughly extract the most important nuggets of knowledge from Chapter 4 of this book. We want to help you shortcut your way to being profoundly well-informed about how Linux handles file input and output.
Cutting through the complexity?
Exactly. We'll meticulously cover everything from the basic ceremony of opening and closing files to the mechanics of reading and writing data, and even delve into how performance is optimized.
There's some really cool optimization tricks in there.
Oh, yeah. All while revealing some truly surprising facts that showcase the sheer ingenuity and foresight of Unix system design principles that are still profoundly relevant today. So, let's kick things off with a concept that might sound abstract, but is honestly one of Linux's most elegant and powerful features: device-independent I/O.
Sound technical, maybe.
It sounds pretty technical, yeah, something you might expect only a kernel developer to obsess over. But in essence, it frees you, the application developer, from needing to know the incredibly tedious and intricate details of every single piece of hardware your program might interact with.
Which is huge.
It's massive. You don't have to write one piece of code to talk to a printer and an entirely different, complex set of instructions to talk to a hard drive or a network card. That's a huge deal.
Exactly, and the historical context here really underscores its genius. Just imagine a world before device independence.
It sounds painful.
Oh, it was. Every application writer would need to understand the unique low-level commands, the specific control registers, the timing nuances for every model of printer, every hard drive, every network interface. It was a nightmare.
Just drivers everywhere, specific to each app.
Basically, yeah. Driver-specific code built into applications, making software incredibly difficult to write, maintain, and port between different machines or hardware configurations.
Okay.
Unix's revolutionary insight was to abstract all that away. The kernel provides a uniform interface, the file extraction. Your applications simply write to a file or read from a file, regardless of whether that file is physically a disk on a hard drive.
Or like the screen.
Or a terminal displaying text, exactly. Yeah. Or a network socket sending data across the internet. Or even a virtual device like DevNull.
Right, the great black hole.
This single powerful idea unleashed an explosion of portable software and is fundamentally why we can run the same applications on such a diverse range of hardware today.
That's a profound impact, making the complexity of the hardware just disappear behind the simple, consistent interface.
It simplifies things dramatically for the programmer.
You mentioned the kernel making this magic happen. We've talked in earlier deep dives about the kernel being the very core, the central brain of a Unix-like system. So how does it manage this incredible feat of device independence? How does it make a physical hard drive with all its spinning platters and read-write heads?
Yeah, all that mechanical stuff.
Look and behave just like a simple text file or a network connection to a running program.
That's where the kernel truly shines, acting as the ultimate intermediary. the traffic cop, if you will.
Okay.
The kernel, which is the foundational software loaded into a protected area of memory called system space at boot, has full, unrestricted, and exclusive access to all the hardware attached to the computer.
Only the kernel gets to talk directly to the hardware.
Correct. It's the only component that can directly communicate with and control these devices. To achieve device independence, the kernel maintains an intricate web of internal system resources.
Like data structures.
Exactly. Sophisticated data structures specifically for I/O, memory management, and tracking the usage of every single device. When a user program needs to perform an I/O operation, say, writing data to a file, it doesn't try to access the hardware directly.
That would be chaos.
Total chaos and insecure. Instead, it makes a system call. As we discussed back in Chapter 2, system calls are the programmatic interface, the secure and controlled gateway.
The API to the kernel?
Precisely. The gateway through which user space applications request services from the kernel. The kernel then intercepts this generic I/O request, translates it into the specific low-level commands required by the particular hardware device involved.
Using the right driver.
Using the right device driver, yes.
Right.
And it handles the actual interaction, using its internal data structures and those drivers. This fundamental separation of concerns, where user programs deal with an abstract file and the kernel handles the concrete device-specific interactions, is absolutely fundamental to the Unix philosophy.
A cornerstone.
Truly a cornerstone of its robustness, security, and flexibility.
Okay, so before we can even begin to open a file, there's sort of an invisible gatekeeper we need to understand. File permissions.
Right, access control.
We've certainly talked about them before, the familiar read, write, and execute bits for the owner, the group, and others, RWX. But the book introduces a really key and maybe often overlooked concept related to file creation. The file creation mask, or umask.
Yes, the umask.
It's a small detail, seemingly, but it has a surprisingly big impact on system security and how new files behave right out of the gate.
This raises an important question. Why do we even need a mask? Why not just have a simple default for newly created files, like maybe wide open or maybe totally closed?
Yeah, why the extra step?
The truth is, when a new file or directory is created, its initial permissions aren't just a random default or simply the most permissive settings possible.
Yeah.
That wouldn't be very secure.
No, probably not.
The mask acts like a filter, or you could think of it as a proactive security blanket. It effectively turns off specific permission bits from the default permissions a newly created file would otherwise receive.
So it subtracts permissions.
Exactly. Think of it as a subtraction.
Yeah.
The system calculates the maximum possible permissions, maybe like RW for a file, and then the mask value dictates which of those bits are removed before the file is actually created.
Okay.
This ensures that newly created files don't accidentally get more permissive access than intended, thereby enhancing system security right from their inception.
Makes sense.
For instance, a common mask value is 0022. The 0 prefix indicates it's an octal number. In octal, 7-bit is ROWX, 6 is RW, 4 is RD. So 0002. The commit corresponds to write permission. This mask removes write permission for the group and others.
Got it. So group can't write, others can't write.
Correct. This means when you create a new text file, it might default to RWRR, owner can read-write, group others can only read, instead of the potentially more open RWRWRT. It's a fundamental proactive security measure.
Prevents accidental oversharing.
Especially in a multi-user environment. Users typically configure their mask in their shell configuration files like .bash or .pro file to set their preferred default security level.
So it's like setting a baseline security level, a minimum standard for all new files and directories. It prevents that accidental oversharing before it even happens, which is, well, a very smart default to have in a system like Linux.
It really is. It's the unsung hero ensuring that baseline security.
Okay, so once we've created a file or accessed an existing one and done our thing, reading, writing, we need to be sure to close it. This might seem obvious, right? Almost trivial, like closing a door behind you.
These are just good manners.
But the book emphasizes why the close system call is not just good manners, but absolutely crucial for both data integrity and efficient system resource management. It's far more vital than it first appears.
Indeed, close is a foundational pillar of robust file I/O. Calling close does several critical things. First, it explicitly breaks the connection between your program and the file. Signals to the kernel, I'm done here.
Okay.
Crucially, it frees the file descriptor that your program was using. That little number we'll talk more about, makes that identifier available for reuse by another open file or another process.
Cleans up resources.
Yes. And if there are no other descriptors pointing to the associated open file description, OFD, which is the kernel's internal representation of an open file instance, then those kernel resources are also freed, the OFD itself is removed, cleaning up system memory.
Got it. But you mentioned data integrity, too.
Yes, and perhaps even more importantly, for files you're writing to, if you fail to call close explicitly, some of the data you intended to write can actually be lost. Gone.
Lost data. Wait, that sounds like a major problem if you're not careful. How exactly does data get lost if my program has already called write? I told it to write.
But telling it isn't the same as it landing on the physical disk immediately. This is due to kernel buffering, a vital performance optimization we'll discuss more later.
Okay, buffering.
When your program calls write to send data to a file, that data isn't always immediately sent directly to the physical disk. That would be incredibly slow and inefficient for every tiny write.
Right, disk is slow.
Very slow compared to memory. So instead, it's often written first to kernel buffers, a temporary, highly optimized storage area within the kernel's memory. The kernel then decides, based on its own sophisticated algorithms, current system load, disk activity, the most optimal time to actually flush that buffer data out to the underlying hardware.
So write returns, but the data might still just be in RAM.
Yeah, it might well be. The close system call, however, acts as the flush and commit operation for your file descriptor. It forces the kernel to immediately write any remaining buffered data for that specific file to the underlying storage device.
Close. It forces the flush.
Exactly. Without this explicit close call, that data might just sit in kernel memory indefinitely, especially if your program terminates abruptly or the system crashes.
Oof. Gone.
In such scenarios, any data that hadn't yet been flushed to disk would simply be lost, never making it to permanent storage. So, close ensures durability and data consistency.
That's a vital, often misunderstood detail. It's not just about cleaning up. It's about making absolutely sure your data is actually saved, persisted. So if close is so critical and it performs such a fundamental action, what could possibly go wrong when you call it? Can it actually fail? It feels like it should always work.
While successful close calls are definitely the norm and you generally expect them to succeed, close can indeed fail. It can return -1 to indicate an error.
Really? How?
It's relatively rare, but it's crucial for robust applications to understand why and handle it.
Yeah.
One common scenario is that a previous write operation might have encountered an underlying disk error. Maybe the disk became full or there was a hardware issue.
A delayed error.
Exactly. The kernel might have been able to buffer the data temporarily and didn't report the error immediately on the write call. But when close is called, it attempts to flush those pending kernel buffers to disk. If it then encounters that previously latent disk error,
Close gets the blame.
close becomes the first system call to report that underlying I/O problem, yes. Other possibilities include asynchronous I/O errors, maybe issues with the file system itself becoming corrupted or unavailable during the flush.
Wow. Okay.
This is why, for critical applications and robust system programming, it's considered good practice to always check the return value of close and handle potential errors. It ensures that any pending issues with the file are fully resolved or, at the very least, explicitly reported to your program, preventing silent data loss or corruption.
Definitely something to remember. Check the return value of close.
Okay, let's unpack this with purpose then. If we want to do anything with a file, read its contents, add new data created from scratch, we first need to establish that connection. That's where the open system call comes in.
The starting point. The book introduces open and also mentions create and open it, but it quickly and rightly points us to open as the fundamental and most versatile system call among them. It's your primary gateway.
Your handshake with the file system for that file.
Yeah, the ceremonial handshake that initiates all subsequent file interaction.
Truly is the primary interface for file operations in Linux, forming the bedrock of all file-based I/O.
When your program calls open, the kernel springs into action. It doesn't just grant access, it sets up a crucial internal data structure called an open file description, OFD, within its memory.
OFD. Right.
This OFD is a central repository of metadata for that specific open instance of the file. It tracks vital information such as the file's current status flags, the specific access mode your program requested, like read-only, write-only, or read-write, and critically, the file offset.
The offset, like a cursor position.
Exactly like a cursor position, yeah. The file offset is essentially a precise pointer that indicates the byte position within the file where the next read or write operation will begin.
Got it. In return for setting all this up, open provides your program with a small, non-negative integer the file descriptor, often called OFD.
Just a number.
Just a small integer, yes. This file descriptor is simply an index into your process's own private file descriptor table, and that table entry then points directly to the OFD that the kernel created.
So the FD is my handle pointing to the kernel's internal info.
Precisely. It's a very clean, efficient, and well-defined way for your program to refer to and interact with a specific open file instance.
So open sets up this whole relationship. It takes a file path, a set of flags, and sometimes a mode. These sound like incredibly important details for telling the kernel exactly what we intend to do. What do these flags tell the kernel? What are some of the most common or important ones?
The flags are absolutely crucial. They are the granular instructions. They are bitwise or read together. You combine them using the pipe symbol usually and pass as an argument to open, precisely controlling how the file is opened and what operations are permitted.
Okay, give me some examples.
All right. Or DUBR. This is fundamental. Open for both reading and writing. If you omit this, you'd specify ordinally for read-only or own-only for write-only. Pretty basic.
Makes sense.
Ocreate. If you want to ensure the file exists, or create if it doesn't, you use ocreate. A very important point here. If ocreate is used, open requires a third argument.
The mode.
The mode, exactly. This argument specifies the permission bits for the newly created file using an octal number like 0644. Remember, mask, the mode sets the initial permissions, and then mask filters them.
Gotcha. 0644 is owner read-write, group others read-only.
Correct. If you use ocreate and forget that third argument, the call will just fail.
Okay, watch out for that. What else?
Ocreate and C. This flag is powerful and potentially dangerous. If the file already exists and you open it with OTUNC for writing, poof.
Wipes it clean.
Instantly. Its contents are truncated to zero length. Everything inside is gone, no warning. This is a common source of accidental data loss for new programmers if they're not absolutely sure.
Yikes. Okay, OTUNC. Handle with care.
Definitely. Then there's OAppend. Essential for things like log files.
So it always writes at the end.
Exactly. It forces all subsequent write operations to happen at the very end of the file, regardless of where the file offset, our internal pointer, currently is. Even if multiple processes are writing, they all append nicely.
Useful for logs. Yeah. Any others stand out?
Well, OEXCL is often used with ocreate. If ocreate is specified and the file already exists, OEXCL makes open fail.
Ah, so it prevents overwriting if you only want to create.
Precisely. It's critical for atomic file creation, like lock files, preventing race conditions where multiple processes try to create the same file simultaneously.
Smart. And you mentioned flags for data integrity.
Right. ODSYNC and OSYNC. These are crucial for things like databases. They force write calls to basically wait until the data is physically on the disk.
Slower, but safer.
Much slower, potentially, because it bypasses some kernel buffering, but much safer against crashes. ODSYNC syncs data, OSYNC syncs data, and metadata. Depends on your needs.
And non-blocking.
On block. Used a lot in network programming or when dealing with pipes. If a read or write can't complete immediately, instead of waiting,
it just returns.
It returns immediately with an error like EGIN or EWOOD block. Lets your program do other things instead of getting stuck waiting for I/O. Fundamental for responsive apps.
Wow, that's a comprehensive toolkit just in the flags. So if I just blindly use ORWR, ocreate, OTRA, and C on an existing file...
You're hitting the nuke button on it.
Yeah, essentially hitting a nuclear reset button on its contents. That's powerful and potentially devastating if you're not absolutely certain. Like saying, open this door. If it's not there, build one. If there's anything inside, throw it all out before I even look.
Precisely. Concise, but carries immense, irreversible implications. Understanding these flags and their combinations is paramount. Now let's dig a little deeper into that file descriptor versus open file description thing. It's subtle, but key.
Okay, FD versus OFD.
Why differentiate? At first glance, they might seem the same. But understanding their relationship is key, especially in multi-process environments. Let's use an analogy. Imagine your local public library.
Okay, I'm at the library.
When you check out a book, you receive a loan slip. That's like your final descriptor. A small, unique identifier for your personal interaction with that specific book. It's local to you.
My FD.
Your FD, exactly. But the physical book itself, with its current page marked where you last left off, any notes about its condition, its status, that's like the open file description maintained by the library, which is the kernel.
The OFD is the kernel's view of the open book.
Exactly. The actual central record of the book's active state. Now, crucially, multiple people can have separate loan slips, file descriptors, for the same physical book. or a file.
Oh,
Well, maybe they're sharing it, or more relevantly in Unix, a process might fork,
yeah,
creating a child process that inherits open file descriptors.
yeah.
Or a process might use dup2 to duplicate a descriptor.
Okay, so multiple FDs can point to the same underlying open file state.
Precisely. Multiple file descriptors, potentially from different processes, can point to the same OFD. This means they share the same file status flags, like OAPND, and, most importantly, the same file offset.
Whoa, so if one process reads, the offset moves for the other process too?
Yes, if one process reads 100 bytes, advancing the shared offset in the OFD, the next read by another process sharing that OFD will pick up immediately after, from byte 101.
That's really important for coordination.
Absolutely. This sharing mechanism is fundamental for understanding how processes can cooperate efficiently on file I/O, allows them to read from or write to the same position sequentially or coordinate access. That's a powerful concept behind many advanced patterns.
That library analogy really clarifies it. The slip is mine, OFD. The book state is shared, OFD. Okay, so once a file's open, we've got our FD, loan slip. How do we actually get data in and out? Read the book, write in the margin.
Basically, yeah.
The book points to read and write as the fundamental workhorses for moving bytes.
They are indeed the fundamental system calls for data transfer, the core of I/O.
The hands and mouth of file I/O.
Good way to put it. So read, FD, buff, and bytes. This call attempts to read up to n bytes of data from the file referred to by FD. The data gets placed into a memory buffer buff that you provide in your program's memory.
My buffer. Okay.
On success, read returns the number of bytes actually read. Could be less than n bytes.
Oh, right. Might hit the end of the file?
Exactly. A return value of 0 means end of file, no more data. If an error occurs, it returns man of 1.
Okay. And write?
Write, FD, buff, n bytes. The mirror image attempts to write up to n bytes of data from your memory buffer buff to the file associated with FD.
And it returns the number of bytes written.
Yes, the number of bytes actually written on success, or majorless 1 if an error occurs. These two functions, read and write, in tandem, form the basis of all direct file data manipulation in Linux.
The return type for both read and write is sizeIt. You mentioned that's a signed size type, not just unsigned int. Why the sign? Why is that important to pay attention to?
You've hit on a critical detail again. It's often a source of subtle bugs if overlooked. sizeIt is signed precisely because it needs to represent two distinct outcomes. A positive number for the count of bytes successfully transferred, which is always 0 or more. Or a specific negative value, typically -1, to signal an error condition. It's absolutely critical for programs to check this return value diligently. Not only check for -1 to detect errors,
And check or no, probably.
and then examine error for the specific error code, yes.
Yep.
But you also need to be aware of something called partial writes.
Partial writes, you mean write. Doesn't always write everything I ask it to.
Exactly. A partial write means write, returned a positive value, so it succeeded, but that value was less than the n bytes you requested.
Huh. Why would that happen?
It isn't necessarily an error in itself, but it means not all of your intended data was transferred in that single call. The kernel managed to write some of it, but not all.
So what causes a partial write, and what should a robust program do? Seems like that could easily lead to incomplete files if you don't handle it.
Absolutely. Partial writes can occur for various reasons. The file might hit a maximum size limit, the disk might literally be full,
Ran out of space mid-write.
yep, or the user's disk quota might be reached. External factors like signals interrupting the system call can also cause them. In these cases, the kernel writes as much as it can before the condition stops it and reports that partial success.
So what's the right way to handle it?
A robust program has a couple of options. It could report an error and exit saying couldn't write everything, or ideally, it should implement a loop.
A loop.
A loop that repeatedly attempts to write the remaining data. You adjust your buffer pointer to start from where the last write left off, decrease the count of bytes to write, and call write again.
Keep trying until it's all written.
Keep trying until all the bytes you intended are written, or until write returns 0, which is odd for write, or -1 indicating a real error. This pattern of handling partial reads and writes is fundamental for data integrity.
Got it. Loop until done or error. Never assume one call does it all.
Never assume, always check the return value.
The book gives a great practical example with splcp1.c, which is a simplified version of the standard keyp command, like a mini CP.
Yeah, a teaching version.
It shows exactly how read and write are used together in a loop to copy data from a source file to a target file. Sounds like a fantastic hands-on way to see this in action.
It's an absolutely foundational learning tool, SPLCP1, precisely because it demonstrates these core concepts fitting together. It meticulously highlights the importance of rigorous error checking, check open, check read, check write at every step, non-negotiable in real code.
Good habits to build.
And while the book's version might simplify the partial write handling for clarity, the structure implicitly shows the need for it. A real key must loop correctly.
Okay. And how does it handle the target file?
Its design uses ocreate to create the target if needed, and OTRUNC to truncate it if it does exist.
Ah, the clobber flag.
Yes, it clobbers overwrites any existing target file without asking. Boom.
Which is maybe not what you always want.
Definitely not always. This behavior, clobbering files, is something the POSIX specification for the actual KP command explicitly addresses. That's why many users instinctively reach for the AI option on CP.
The interactive mode, overwrite file X.
Exactly. I asked for confirmation. So SPLCP1 is a great example of how even a seemingly simple utility has complex underlying design decisions impacting user experience and data safety.
It's a powerful reminder that even simple commands we use every day, like cleep, have complex and carefully considered underpinnings. And it's essential to understand the potential for data loss if you're not aware of how these flags and calls work.
Absolutely underscores the value of digging deep.
Okay, here's where it gets really interesting, I think, and where intuition can sometimes lead us astray. Performance.
Yes, the need for speed.
We might naturally think that using read and write directly, maybe read in one byte at a time or in very small chunks, would be the most immediate and therefore fastest way. Get the data moving ASAP.
Use logical right, minimize delay.
But the book really delves into how buffering significantly impacts and often improves performance. It uses an experiment with SPLCP2.ca modification of SPLCP1 that lets you change the buffer size to really illustrate this.
This is a crucial area. The interplay between your application and the OS is paramount here. The key insight is larger buffer sizes generally mean fewer system calls are made to copy the same total amount of data.
Fewer calls, okay.
Let's take that 4 MB file example again. If you copy it using a tiny, say, 1 byte buffer, that's 4 million read calls and 4 million write calls.
8 million system calls, that sounds slow.
Incredibly slow. Now use a 4 KB buffer in your PLCP2 program. You'd involve maybe 1,000 read calls and 1,000 write calls.
Okay, 2,000 calls, much better.
Much better. Double your application's buffer to 8 KB. Now maybe 500 read and 500 write calls, half the calls again.
Right.
Since each system call involves a context switch from user space to kernel space and back a relatively expensive operation with overhead, intuitively, larger buffers should be faster. Fewer expensive transitions, kernel handles bigger chunks.
That makes sense. Fewer expensive context switches, less overhead. But it's not just about our program's buffer size, is it? You mentioned earlier the kernel is also doing clever things behind the scenes.
Exactly. That's the other half of the equation.
This distinction is crucial, right? Application buffer versus kernel buffer.
Vital for deep understanding. When your user process calls read or write for disk data, the kernel usually doesn't transfer data directly between the physical disk hardware and your program's buffer.
No direct path.
Not usually. That would be inefficient and cause contention. Instead, the kernel acts as a sophisticated intermediary. It moves data between the disk and a dedicated, highly optimized kernel memory storage area called the buffer cache, or page cache in modern Linux, same idea.
The buffer cache in kernel memory. So for a read, the data doesn't jump straight from the disk into my buffer. It goes disk, kernel buffer cache, my buffer.
Correct. The kernel reads from disk into its cache, then copies from its cache into your buffer.
And for a write, my buffer guess, kernel buffer cache.
And then later, kernel buffer cache disk.
Ah, later, asynchronously.
Often, yes. This system, buffering the kernel's strategic use of its buffer cache, significantly improves overall I/O performance in several key ways.
How?
Firstly, it lets the kernel batch multiple small disk operations into larger, more efficient ones. Fewer physical disk seeks, which are slow.
Okay, batching.
Secondly, and very powerfully, it caches frequently accessed data in memory. If your program or another program requests data that's already in the buffer cache.
No disk access needed.
Exactly. The kernel provides it directly from fast memory. Huge speed up. This caching also includes write-behind buffering, where writes are held in cache and written to disk asynchronously, letting your program continue immediately.
So the kernel is constantly juggling this cache for speed and efficiency.
It's a complex, highly optimized system, constantly balancing speed with data durability concerns.
That intricate dance between my buffer and the kernel's buffer cache is fascinating. The book describes running an experiment with SPALE-CP2, testing different buffer sizes, recording elapsed time, user time, system time. What did results like that typically show? What's the takeaway?
The results, like those you'd see in Table 4.3 in the book, show a really interesting nonlinear pattern. Initially, as you increase the buffer size in your SPALE-CP2 program,
Performance gets better.
yes, the elapsed time for copying the file generally decreases significantly. This initial improvement is largely due to reducing system call overhead, just like we discussed, fewer context switches.
Okay, makes sense. But does it keep getting better indefinitely? Bigger is always better.
No.
Yeah.
That's the catch. Beyond a certain optimal point, and this point depends on disk block size, kernel cache behavior, CPU cache lines, lots of factors.
The sweet spot.
Exactly. Beyond that sweet spot, the gains diminish. Sometimes performance might even slightly reverse or just plateau.
Why would it plateau or get worse?
Because once your application's buffer is large enough to effectively utilize the kernel's buffering and align with disk blocks, making it even larger might not help much. It could even introduce new overheads, like more memory copying within the kernel, or maybe messing with CPU cache efficiency if the buffers get huge.
So it's a balancing act.
It's a delicate balance.
Yeah.
It beautifully illustrates that more system calls isn't always slower if they're optimized well by the kernel, and fewer calls isn't always faster if the buffers become inefficiently large or misaligned. You have to consider both your app and the kernel.
So performance isn't just about maximizing buffer size. It's about finding that optimal alignment with how the kernel works. Now, shifting gears slightly, if read and write automatically advance that file offset, like a tape head moving forward.
Sequentially, yes.
How do we gain precise control? What if I want to jump directly to the middle of a huge log file or read the last 10 bytes rather than reading everything from the start?
That's where else comes in. Use your navigation tool.
Okay.
Lseek allows programs to explicitly move the file, offset that crucial internal pointer in the OFD to a specific arbitrary position within the file.
Reposition the cursor.
Exactly. When a file is first opened, the offset is at byte 0, the beginning, unless you used oapn.lseek. Let you change that. Without it, I/O would be strictly sequential.
How do we tell lseek where to go? What are the controls?
It's very flexible. It takes 3 arguments: the file descriptor, FD, an offset value, which is a number of bytes, and a whence argument.
Whence? Like from where?
Precisely.
Well,
Whence specifies how that offset should be interpreted. There are 3 main options, defined as symbolic constants.
okay.
Seek set. This interprets the offset as an absolute position from the very beginning of the file, byte 0. So lseek FD124 seek set moves the offset to byte 1024.
Got it. Absolute position.
Seeker. This interprets the offset as a relative change from the current file access position.
Yeah.
lseek FD100 seeker
Yeah.
moves 100 bytes forward. lseek FD nanocone seeker P moves 10 bytes backward.
Relative jump. Useful.
Seekend. This interprets the offset as relative to the end of the file. So lseek FD0 seekend moves the offset to the end of the file. lseek FD-1 seekend moves to the very last byte of the file.
Ah. And you mentioned a trick using seekend.
Yes, a
Yeah.
very common and clever trick.
Uh-huh.
Calling lseek FD0 seekend moves the offset to the ends, and the value returned by lseek itself is the new offset position, which is the size of the file in bytes.
Whoa, that's neat. Find the size without reading anything.
Super efficient way to get the file size.
Mm-hmm.
Just remember, lseek only works on files that are seekable, regular files on disk, basically. You can't seek on pipes, network sockets, or terminals. They're just streams.
Right, no random access on a stream. Makes sense. That size trick is great. Now, what happens if you seek past the current end of the file, like lseek, LFD1000 seekend, on a file that's only 500 bytes long, and then you write something?
Now you're getting into something really cool.
The book mentions file holes. This sounds like a surprising fact, almost like magic storage.
It absolutely is a fascinating detail and a brilliant storage optimization built into Unix-like file systems. If you lseek beyond the current end of the file and then perform a write, a file hole is created.
A hole. What does that mean?
It means the space between the old end of the file and the new position where you started writing is conceptually filled with zeros. If you were to read from that gap later, you'd get back bytes with value 0.
Okay, filled with zeros. But
here's the magic. No actual disk blocks are allocated for that hole on the physical storage device. The kernel simply records metadata saying, this range is sparse, treat it as zeros.
so the file looks bigger, but doesn't use the disk space for the empty parts.
Exactly. Disk blocks are only allocated on demand if and when you later explicitly write data into that hole.
Yeah.
It's a highly efficient way to handle large files that are potentially sparse files with long stretches of empty, zero-filled data.
Can you give an example where this is useful?
Oh, definitely. Think about virtual machine disk images. You might create a virtual disk that's notionally 100 gigabit, but initially, the guest OS has only written maybe 10 gigabits of actual data. File holes allow the file system to represent that 100 gigabit logical size without actually wasting 90 gigabits of physical disk space.
Wow, that saves a ton of space.
Huge savings.
Yeah.
Same applies to large database files that might be pre-allocated but are mostly empty initially, or certain scientific data formats. If you use ls-l on a sparse file, it shows the big logical size, including holes.
Okay.
But if you use a command like do block size 1 disk usage, it reveals the actual disk space allocated, which might be much, much less.
Because the holes don't count in do.
Right. It's a testament to the sophisticated, intelligent storage management designed into Linux, conserves resources, improves efficiency, all quite transparently.
That's incredible. A layer of optimization, completely invisible most of the time, but hugely impactful. Okay, one last area. Earlier we mentioned permissions as a gatekeeper. The book briefly touches on how processes manage credentials. How does the kernel actually use user IDs and group IDs to decide if my process can touch a file?
This is fundamental to the Unix security model, ensuring processes only access what they're allowed to. Processes in Linux operate with a set of user IDs and group IDs. It's not just one ID.
More than one.
Yes, there's a real user ID who launched it, an effective user ID, the ID used for permission checks, which can change via Situate programs like sudo, a saved user ID to remember the original effective ID, and, uniquely in Linux, a file system user ID.
File system user ID.
Often it's the same as the effective user ID, but it can be set independently. It's the primary ID Linux uses for file system access checks. When a process tries to access a file read, write, execute a day, the kernel performs a rigorous check.
Against the file's permission.
Yes, it uses the process's credentials, specifically the file system user ID and the process's group IDs, and compares them against the file's owner, group, and permission bits, RWX for owner, group, other.
So it asks, does this process's ID match the owner? If so, check owner permissions. If not, does it match the group? Check group permissions. Otherwise, check other permissions.
That's basically the logic, yes. Is the requested operation, read, write, or execute, permitted for this process, given its identity and the file's access control list? If the check fails at any point based on the file system UID and groups,
Access denied.
access denied, unequivocally. This protects system integrity, user data, enforces the principle of least privilege right at the core of every single file operation.
We've just taken an incredibly deep dive there into the basic concepts of file I/O in Linux, drawing these invaluable insights from Stuart N. Weiss's System Programming in Linux.
Covered a lot of ground.
We really did. Systematically covered everything from the foundational importance of device independence, the crucial close call for data durability,
Don't forget, click.
never forget close, to the intricate mechanics of open, read, write, and then that fascinating performance role of kernel buffering, the precision of listing, and even file holes.
Understanding these fundamentals is just so much more than academic, It demystifies how your computer handles files every single second, yes, but it also gives you the essential building blocks for writing better software.
Robust, efficient, secure software.
Exactly. Whether you're debugging an application that's mysteriously losing data, trying to optimize a disk-intensive task, or just plain curious about what happens when you click Save. These concepts are foundational. The way Linux uses kernel buffers, for example, directly impacts system responsiveness, the perceived speed of your apps. And file holes show how efficiency is achieved even in simple operations. These principles are silently at play, constantly shaping your experience.
Even if you never write a line of C code yourself.
Precisely.
So here's something to mull over, building on these decades of robust design we've just explored. Given the elegant simplicity and enduring power of device-independent I/O,
That core abstraction.
yeah, and coupled with the sophisticated performance optimizations like kernel buffering and sparse files, how might these basic concepts, perfected over decades in Unix and Linux, continue to influence the design of future systems?
Where do these ideas go next?
Right. Even more complex, distributed systems or totally novel storage technologies. Could the lessons from Linux's humble file I/O still shape how we think about data access and resource management in entirely new computing paradigms? Maybe in quantum computing, where information is different, or massive decentralized storage networks.
It's fascinating to think how enduring those core principles might be. Abstraction, efficiency, managing resources carefully.
Food for thought, indeed. how foundational principles echo far into the future. Thank you for joining us on this deep dive into the heart of Linux File I/O. We really hope you gained some truly valuable insights and had maybe more than a few aha moments along the way.
Hope it was useful.
Until next time, keep learning, keep exploring, and keep questioning what's happening beneath the surface.